Okay, everybody, good evening once again. So, in this morning's lecture, we spent some time looking at detail at two different types of convergence for sequences of functions. So we have pointwise convergence and uniform convergence. Uniform convergence is the stronger type of convergence for sequence of functions. So in this context, the sequence of functions we're thinking about are the partial sums of the Fourier series. So in here, so this is a kind of this is coming from a particular example. This is just a single sum. A general Fourier series, you'd have the sine sum and the cosine sum. But an infinite series of functions, it's converging to its limit function. But what's the definition of convergence for a series? It's the limit of the sequence of partial sums. Okay. So by making the upper bound of the summation be some finite quantity and letting that converge to infinity, you get the sequence of partial sum functions. We looked at two different types of convergence for sequences of functions. We had the second type, this uniform convergence, where it's the same rate of, or where there exists a rate of convergence that applies across the whole domain of the function. That was a nicer kind of convergence, a stronger kind of convergence. It's called uniform convergence, and it allows one to make moves like this. Okay? In this particular example, of course, this move where we differentiated an infinite sum by differentiating it term by term and adding all the parts together, that led us to a contradiction in this particular example, where we set this kind of nonsense type statement where 1 is the same as 2 times 1 minus 1 plus 1 minus 1. So you get this non-convergent series on the right-hand side. The reason we arrived at that contradiction because the Fourier series for this particular function that we're focusing on, is the x function, this isn't uniformly convergent. Isn't uniformly convergent because the function is essentially a point of discontinuity at the boundary of the interval from minus pi to pi. But when we do have this nicer form of convergence, we're allowed to do things like this. So we can, if this series did converge uniformly, it depends on what the coefficients are, it depends on what the Fourier, what the function is that you're taking the Fourier series of. When it does converge uniformly, we are allowed to differentiate infinite series term by term. Okay? You're always allowed to differentiate finite series term by term. It's just the linearity property of differentiation. But it can be extended to infinite linear combinations when the convergence is uniform. It's often a delicate matter, and it's often a crucial matter in mathematical analysis, the close technical discussion of functions of real numbers about what you can and can't do to infinite collections. Okay? Because very often there's reasonable properties you can do to finite collections, like applying the linearity of differentiation, but extending those things to infinite collections often has to be handled carefully. So we finished then this morning by considering the statement of Parseval's theorem, which I encouraged you to think about as a generalization or an extension to this context of the familiar idea of the length of a vector being, or the square of the length of a vector being the sum of the squares of the components of the vector. When you're using an orthonormal basis for the vector space. So let's look closely at what it says. It says when we've got a Fourier series, this is the general form of a Fourier series here. When we've got a Fourier series that does converge uniformly, when we've got a Fourier series that does converge uniformly, we get this equation here, okay, which is a nice equation that relates the integral of the square of the function. You can think of as like being the norm squared of the function. The integral of the square of the function being essentially this sum of squares expression of the Fourier coefficients. Okay. So we can say a little bit about the proof of this. It's basically just an application of this uniform convergence definition, and then we'll have a look at the example that's following it, example 3.9. Okay? So we're discussing here a proof justification for Parseval's theorem. So if we look at this integral on the left-hand side, we're going to consider the integral from minus pi to pi of the square of f of x. Okay, so we're just going to consider this integral fairly directly, but in using a similar approach that we used for establishing the Fourier coefficients. See, this is the square of f of x. One of the f's I'm going to leave alone as quantity f of x itself, but the other factor of f of x that's multiplying this to give you the square, I'm going to think of as the Fourier series for the function. So this is your half a naught plus the sum of all your an's cosine nx plus the sum of all your bn's times sine of nx. We're assuming we have this Fourier series for the function, so we can replace the function by this. Now we're assuming here slightly stronger that that the convergence is uniform. So we're told the convergence is uniform, and what we're looking at now is, if you imagine multiplying out the bracket, is we've got a linear combination inside the integral, a doubly infinite, essentially, linear combination of functions. And we want to take the integral of it. So here is where we can use the uniform convergence. So this is an integral of an infinite linear combination of functions. Which by the uniform convergence, that's going to allow us to integrate it term by term. Okay? To apply the linearity property, basically, of integration. Okay? There'd be no conceptual problem if this was just a finite linear combination inside. Then you just use the regular linearity property of integration to say the integral of a sum is the sum of the integrals. But to apply it to an infinite one, we need to have this stronger type of convergence, such as uniform convergence. Okay? So I can apply linearity now. So I can say this is a half of a naught times the integral of f of x dx. All these integrals are minus pi to pi. See, because when you multiply this f of x by this first term here, you have a half a naught f of x. Applying the linearity means I'm going to have this integral here. And then I have f of x times this infinite sum here. Okay. Got f of x times this infinite sum here. Now the f of x doesn't depend on the summation index n. So the f of x can be multiplied in and multiply the summand of the sum. Then we got the integral of an infinite sum. I can use the uniform convergence to say that's the sum, the infinite sum of the integrals. So this will become an. An doesn't depend on the integral, times the sum from n equals 1 to infinity of the integral from minus pi to pi of f of x cosine nx dx. So the integration moves inside the sum. So I got the sum of the integrals But then the AN doesn't depend on x, so it can pop outside. Sorry, that should be inside the sum. Yeah, my AN should be inside the sum. It can pop outside of the integral though, because the AN doesn't depend on x, so it can move outside of the integral. And then you got the similar thing for sine terms. You've got the sum from n equals 1 to infinity, Bn times the integral minus pi to pi of f of x sine f of x. But those integrals look extremely familiar to us. Okay? The integral of the function. The integral of the function times the cosine nx function. The integral of the function times the sine nx function. Those three this single integral and these infinite collections of integrals, they're exactly the integrals that occur in the Fourier coefficient formula. Okay? Notice the integrals are the integrals appearing. These are the integrals from the formulae for A0, AN, Bn. Okay, that define these Fourier coefficients. If you look back at what the formulae actually are, this integral here, it's 1 over pi times this integral gives us the quantity A0. And it's 1 over pi times this integral that gives us the quantity AN. So this sum that I'm developing here will become a half A0 times pi A0. And then here you've got sum of n equals 1 to infinity, AN times pi of AN. And the second sum, where you've got Bn times pi Bn. And you see you more or less got the right-hand side of Parseval's theorem here. So we've got, there's a factor of pi and everything here, so we can take that out. Got a half A0 squared, plus the sum of the AN squared, plus the sum of the Bn squared. So I can just stick those on there. Technically, I've done something else here, is I've reordered these sums kind of that I've collapsed together the term like that, but that's okay because they're sums of positive terms, so they are going to be absolutely convergent. So that's just another little technical matter that's gone on there. Generally, if you've got sums of terms, some of which are negative, some of which are positive, you can't automatically reorder the infinite sums. You need to know that the sums of the series are absolutely convergent. Because they're sums of squared quantities, AN squared, Bn squared, they will automatically, if they're convergent, they will be absolutely. So what we've got there is basically Parseval's theorem. The way it's stated in the theorem is just with the 1 over pi on the left-hand side and this quantity on the right-hand side. So that's the end of that argument. Okay, so let's have a look at example 3.9, which is an example of the application of this theorem to a certain Fourier series. We'll have a look at the application of Parseval's theorem, and then we might have a look at actually deriving the Fourier series for this new function. It's another example. It's a good example of working with the integrals and deriving a Fourier series. And it's a little bit more complicated than some of the other ones we've seen. So looking at example 3.9, so this deals with a function that's called, and this terminology comes from the kind of signal processing, it's the halfway rectified sine wave. Okay? The halfway rectified sine wave. So this is the function that's going to be, it's more or less the sine wave, but the first half of it, and this is what the rectification is, the first half of it is kind of nullified. So starting at minus pi and going to 0, we've just got the 0. And then we pick up the sine function. And that would continue on periodically. So it'd be 0 and then pi. 0, sorry, and then the sine function. And then the sine function. So the limits here would be, the points in the axis would be minus pi, 0, pi, 2 pi, 3 pi, and so on. Bit small. Okay. So on the interval minus pi to pi, this function is defined as 0 for x in minus pi to 0, and it's defined as sine of x, whatever that is, for x in the interval 0 to pi. So now we're just given the Fourier series for this in the question. As I say, afterwards we might think about how we might derive that Fourier series, working from the Fourier coefficient formula. So this has the Fourier series f of x, and it's given here in the question, so it's 1 over pi. This is just going to be a straight application of Parseval's theorem. This is rather curious. It has a single sine term and then a whole bunch of cosine terms. And the coefficient is this curious one, 1 over 4n squared minus 1. And it's not cosine of nx, but cosine of 2nx. So it's actually only picking up the cosine functions where the index is even, actually, 2 times n. So this was the Fourier series. So the exercise is use Parseval's theorem to find the sum of the series, by a curious series. So use Parseval to evaluate sum of the squares, the reciprocals of the squares of these quantities. So first of all, we would have to explain why, or to justify why Parseval's theorem is applicable here. Okay. So this appeals back to that previous theorem that we looked at this morning, theorem 3.6. So by theorem 3.6, this f this function f has a Fourier series which converges uniformly to it. Okay? Has a Fourier series with uniform convergence. Because there's 3 conditions you have to list off for the application of theorem 3.6, all of which can be just judged from the definition of the function. The function f is certainly continuous. Doesn't make any sudden jump in values. It's just one continuous green line, the graph of the function. It is continuous. Its derivative is piecewise continuous. Its derivative is not continuous, but it is piecewise continuous. I could trace over this function. I could trace over this function on the graph. But so we got the original function in green. We could put the derivative of f in black. See, when the function x is 0, it's constant, so its derivative is 0 also. But then it starts increasing, and it starts increasing at the rate 1, of course. And at this point it's 0, and then it's down to decreasing at the rate 1. Of course, this what I've drawn here, of course, is the cosine function over this interval, because the derivative of the sine function is the cosine function. Oops, it should be that high. But sorry, it should be more like it should be at height 1. So be more like this. Oh, that's awful, but I'll draw it better here. So it's coming like cosine function. So the derivative is certainly, yeah, okay, I've kind of completely obscured everything there, but the derivative is not continuous. The derivative has these jumps in it, jump, jump, but it's piecewise continuous. It's made of just a few continuous bits glued together. So very simply, the derivative of f has the values 0 and cosine of f. So df dx is piecewise continuous because it's equal to 0 or cosine of x. And lastly, the third part of theorem 3.6 was that the function doesn't have any kind of tricksy discontinuous points at the boundary. It does agree with itself on its boundary. It starts off at the 0 value at the start of minus pi, and it returns to the 0 value at the end of the interval. Okay, so it matches at its boundary. And about 0. So these were the three conditions for theorem 3.6. So this guarantees that this Fourier series is converging uniformly. So we can apply Parseval's theorem. Piecewise.
Oh, okay.
Piecewise.
I can see that.
So let's apply it. It says so one over 2 pi times the integral minus pi to pi of f of x squared dx. We'll worry about what that integral is in a moment. So that's the left-hand side of Parseval's theorem. We'll return to that integral in a moment. But on the right-hand side, we just have a quarter of the square of a naught. So a naught is, so this is a half of a naught. So a naught is 2 over pi, I believe. Yeah, a naught is 2 over pi. So a naught squared will be 4 over pi squared. That's 4 over pi squared. And the right-hand side, so then we've got a half times the sum of the squares of all the ANs and BNs. Now there's only one B quantity, B1, which is B1 is a half. So B1 squared will be a quarter, and then a half of that will be an eighth. We got an eighth here. And then we got a half times the sum from n equals 1 to infinity of the square of all the AN coefficients. So the AN coefficients only occur. Oh, we just got to be careful here. So what is the AN? Well, the ANs only occur when n is even. Okay. The ANs occur only when n is even, because we only get the 2n index here. So when that 2n is even, so the whole AN coefficient is minus 2 over pi times this fraction. So this fraction is, well, that 4n squared is actually the square of 2n. Okay. So I could put this as minus 2 over I times 1 over the square of 2n minus 1. And it's all that quantity squared, because it's all the an squared. So tidying up this slightly here, we'd have 1 over pi squared plus 1 over 8. And this, we should tidy this up a little bit. We're going to have a half here, but you see the 4 over pi squared can come out to the front. Because when you square this bracket, you get a 4 over pi squared. That can come out. So it'll be 4 over 2 will be 2 over pi squared. And then you're left with the sum from n equals 1 to infinity of the square of this part. So I can write that now again as 4n squared minus 1, all of it squared. So the direction in the question, so you just got to be very careful with applying Parseval's theorem, reading off the coefficients, squaring them, and doing the appropriate things to them. So you see this series here is exactly the series that we were asked to evaluate. Okay, it's essentially the main part, or some kind of scaling at the front. It's the main part of the sum of the squares of all the coefficients in the Fourier series. Of course, we can't evaluate this yet until we have a value for the left-hand side. Okay. This quantity in the right-hand side is some constants added and multiplied, and the series of interest. So to evaluate the series of interest, I can maneuver all these things over to the other side as soon as I know what the other side is. Okay. So the integral on the left-hand side is 1 over 2 pi, the integral minus pi to pi, the square of f of x. We see f of x as this piecewise definition. It's 0 in the first half of the integral. Well, you square 0, you still got 0, and you integrate 0, that's not going to generate anything. So this becomes the integral from 0 to pi. It's only interesting on the second half of the integral, and then it's the sine squared function. So we're integrating sine squared. Now we can use a formula, standard trigonometric formula, that sine squared of something is, what is it, 1/2 of 1 minus the cosine of twice the angle. Standard trigonometric formula, which will basically turn it into constants and cosine, which I'll be able to integrate. But I get a half there. That will come out and make this 1 over 4 pi. And then I can integrate these terms, and I'll get an x minus the sine of 2x over 2, evaluated at 0 and 0 and pi. Now what's the value of that? Well, you see the sine part, you're only going to be evaluating at 0 and pi. These are, again, our integer multiples of pi, so those sine values will always be 0. And evaluating the x part will give you the quantity pi. So you're evaluating it at pi minus the evaluation at 0. Okay. Let's get the quantity pi. We'll cancel with the pi at the front and just leave us with 1. Okay, so again, the sine part is just going to evaluate to 0. So finally, then I've got a quarter on the left-hand side of this equation. I've got a quarter on the left-hand side, so I can just maneuver everything across to basically solve this. what do we get? We get the sum of all this, 4n squared, sorry, the sum of 1 over 4n squared minus 1, all of it squared. Sum from n equals 1 to infinity. Well, you move the 8th over, it becomes minus an 8th. So a quarter minus an 8th is an 8th. So you get an 8th on the left-hand side, minus 1 over pi squared. And then you have to cross multiply by pi squared over 2. So you get pi squared over 2 multiplied by an 8th minus 1 over pi squared, I think. Which gives us pi squared over 16 minus a half. Does it appear? Again, is another one of these really curious infinite series expansions for, well, not quite pi, but the square of pi. Okay. Okay, so it's really intriguing how pi or pi squared and so on can arise out of these infinite series of these rational, nice, orderly, rational progressions. So as a follow-up exercise for that, I would set yourself the exercise to derive the given Fourier series for the halfway rectified sine function. Okay, it's a good exercise in working with the integrals in the Fourier series coefficient formulae, and this might be slightly more involved than some of the other ones that we've looked at. Yeah, the halfway rectified sine. Okay, and it is slightly curious that there's just a single sine function in the Fourier series, although it's not that curious kind of when you compare it to the function itself. The halfway rectified sine function in green, because this sine part of it exactly matches the sine function, all you need to generate it really is just the function sine of x, basically. All this other part, this infinite collection of cosine functions, that's there to generate the zero value across the zero half of the integral. And it will generate a similar constant value. Yeah, it'll be interesting what that generates on the right-hand side. It'll generate essentially just some constant value on the right-hand side, which gets scaled away and subtracted away here to return us to basically the half of sine x, to the sine x on the right-hand side. I might generate a sine part. I might generate actually some sine part on the right-hand side as well. Okay, but I might leave that with you as an exercise, or it's something you could pick up in the tutorials this week. I'll pass it on to the other tutors, Frank and Stephen, in their groups. I might finish a bit early this evening, so I'll stick around if you got any questions. I'm a bit hoarse. Inside my voice. Well, feel free to come and ask questions if you need. So in my remaining sessions, both this week, well, I've got a tutorial this week, but in my lecture next week, and And then when we return after Easter, I'll do various revision activities, focusing on the past papers, talking through solutions of those, and answering any questions people might have as well. I'll be doing some past exam questions.